leave some marker over here. So at this very same spot, leave a marker which is called P. Right? But then you're asked by a friend to describe the position of P. To describe the position of P, you give a coordinate of P, right? Then the question arises, then you want to decide on whether you describe a coordinate with respect to this coordinate system or with respect to that coordinate system, okay? Let's say with respect to this coordinate system, it's x, right? But then with respect to that coordinate system, what is the same coordinate at the same point? Apparently it's x plus epsilon. Okay, you see that point here? So we can write that x prime is equal to x plus epsilon, like that, okay? Now, if we are talking about a three-dimensional picture in here, then obviously I have the more general description. X prime I is equal to x I plus epsilon I. Here I'm kind of talking about the same epsilon that we have been talking about in this earlier situation. There's a new x-coordinate. The new x-coordinate is related to the old x-coordinate by a simple translation of a constant amount. All three coordinates get translated by the same constant amount. The value of the function psi x, okay, at this point has to be equal to the value of this different function at the different point. You agree with that statement? Okay. Now notice the dependence on the coordinates. For the old function, it depends on the old. You write it in terms of the old coordinates. For the new function, for the same point, if you want to make the two of them equal to each other in value, then it has to be x prime. Like so. Soak that in a little bit. Take that in a little bit. This is important, okay? The idea is this. I'm going to try to come up with an operator that changes the old function to the new function. The operator is to represent a certain amount for the translation, okay? And the two are equal to each other so that this particular quantity, which happens to be a scalar function in here, has scalar tensorial properties, which means that under a change of coordinates, this function transforms like a rank 0 tensor. In other words, the functional value at the new position is equal to the functional value of the old function at the old position. When something like this happens, we say that the function psi of x transforms like a scalar, okay? If it transforms like a tensor quantity, then you have to go back to your classical mechanics book, chapter 1, and those, you would have a bunch of indices, right? A bunch of indices T prime, which is now a tensor field, which would then have to be functions of the various x prime i's. Okay, ij would have to be used with some transformation of t, kl, and kl here you sum over, and then it's xi, like that. Okay?
Dr. Lam,
yeah.
You said the operator transforms like rank 0 2 tensor?
No. The operator will transform all tensors according to the tensorial rule of transformation. This is what happens to a scalar. It is not changed. If it were a tensor, then there would have to be some transformation matrices, right? Remember that big box equation? For those of you that have taken my classical mechanics courses, that big box equation in chapter 1. Now, of course, in that box equation, we assume that the tensors were just constant tensors, right? But here we are talking about tensor fields, of which the scalar function is a particular kind. A scalar function is a rank 0 tensor field. It is a field because that quantity depends on the position in a certain space. Okay? So in this case, we say that in quantum mechanics, the wave function transforms like a scalar. Okay? Now here comes the question. Here comes the question. Supposing I write this new function, but I want to express it in terms of the old coordinates, okay? And I'm going to try to write it like this, that this is some operator which I'm going to call U. The operator is the operator that produces infinitesimal transformations. And so I use this operator, supposedly I'm going to build this operator so that when I use that to operate on the old function, it gives me the new function, but note that the variables in here are the same, okay, like so. Now this is different, slightly different from this requirement in here, but psi prime x prime is, the requirement is psi prime at the new variables is equal to psi at the old variables, okay? And by this requirement in here, you see, I want to write this as psi at what? The old variable is related to the new variable by this. This is a new variable, this is the old variable, okay?
X prime I minus.
So it must be x prime I
Minus.
minus. Very good. You see that? The minus sign is important. Okay? The one is related to the other by the you get the new variable by adding epsilon to the old variable, right? So obviously by adding epsilon to the old variable, you get to the new variable. Okay? The new variable is always related to the old variable by adding epsilon to the old variable. Okay? So if you think of this as a mathematical problem, if you think of this as a requirement which says that scalar functions have to transform like this, then our task at this point is to be able to cook up a differential operator, an operator which represents, which actually this U needs to take. Okay? I use the symbol U for a good reason. U stands for unitary. You know that in quantum mechanics, the important operators that change the systems because of the requirement of probability, requirement of conservation of probabilities. Mathematically, we can only choose what I call unitary operators. Now, I will not define exactly what is meant by unitary operator at this point, but let me just say that unitary operators are the operators which describe changes for you, a physical system, changes in time, changes in space, and so on and so forth. Okay? Yeah?
Can you explain why it's x I minus, epsilon I again?
Because the new variable is related to the old variable by adding epsilon to the new variable. Okay? So if you add epsilon to this, it produces what it ought to. So, psi prime of something is equal to psi of something else. And you obtain this by adding epsilon to this thing in here.
Okay.
Yeah.
Shouldn't that be psi prime x prime I?
Yeah.
No, I'm going to write it. I'm going to require it to write it as just.
You're writing it in terms of.
I'm writing it in terms of just some general variable. Okay. I don't want to use my. Okay. The idea is, I mean, this is a function, right?
Mm-hmm.
So I'm writing this thing in here basically. Okay. I'm writing this thing in here, this requirement in here. That's all. Okay. I mean, side xi is just a name for a coordinate, right? Is that okay? All right. It's kind of like I'm renaming x prime by x in here. Okay. And by this requirement in here, which is again the requirement for the wave function, that the wave function has to transform like a scalar quantity, I come up with this mathematical condition in here. And right now, as I said, the task is to construct mathematical expression for this unitary operator. Okay, so this is a particular unitary operator. Let's see what that is. So you take a function, you operate on it using a unitary operator, and it's a differential operator. You produce a new function, and the new function is this x psi prime. The old function is psi, the new function is psi prime. Two different functions. Okay, you take this unitary operator, let it work on the old function, you get the new function. Okay, But the requirement is that that unitary operator produces a translation. So that's what that is. So in order to build a unitary operator, all we have to do is to Taylor transform this and keep only the lowest order terms, right? And you know that when you Taylor transform, you just keep terms of the first derivative side. That's where the momentum operator comes in. Because the momentum operator is the first derivative of psi, okay? The first, I'm gonna write it down. This is by Taylor expansion, right? So this is psi at a neighboring position to xi, of course, is equal to psi at xi minus epsilon I, okay? And it must be d with respect to xi, so this I is summed over, so you have to differentiate it with respect to all three variables, and then sum over because there are three epsilons in here, psi, plus terms that are higher order than the first one in epsilon, which we are going to ignore, assuming that this is an infinitesimal translation. Okay? Okay. Okay, let me just write this a little bit differently now. And so that I'm requiring this to be my u, which obviously has to depend on the particular translation, operating on the old wave function must be equal to the old wave function itself or something else, which is a change in the wave function. I'm now going to write this in terms of the momentum operator given by this expression in here. Okay? I'm going to write my gradient in terms of the momentum operator. So I'm just multiplying it by some i's and some and so on and so forth. And it's very simple. You see that this is equal to minus I. Now this I is the imaginary unit, it's not tensorial index. I hope you won't confuse the two. Is that okay? Using that expression with the h bar stuck in, okay? P is equal to minus I h bar, and so it all works out, okay? To be like that, to be just like that. Okay? And so, now, at this point, you can kind of factor out the psi, just, ignoring all the higher order terms in epsilon. My unitary operator, corresponding to an infinitesimal translation, can now be written like this. The identity operator minus I epsilon I pi divided by h bar. Everything operating on psi. Psi is a scalar function, does not have an index. The only places where indices come in are just the three components of the linear momentum operator and the three components of the translation. Okay, this is to be summed over like this. It's kind of like you first translate it along the x direction, then you translate it along the y direction, then you translate it along the z direction, add them up all together, you get a total translation. Okay?
I'm a little bit confused, but because you divide the IH into
P is equal to
IH.
P is equal to what? Minus I h bar di. Okay. So you have minus I h bar multiplied by the h cancels out, one on top, one on the bottom, minus I squared minus 1. So multiplied by this minus 1 gives you a plus 1, so it leaves this minus sign.
Okay, that's what I
Okay? So, I mean, the things equal like this. Okay, so work it out carefully, you'll see that this is the answer. So you compare the left and right hand sides of this equation, obviously this guy can be interpreted as a unitary operator. Okay? Remember the one in here, this expression stands for the identity operator. The identity operator does not do anything to the thing that it acts on, okay? So one acts on psi is just psi itself. But then the second thing does change it a little bit because it differentiates it, okay? Yeah?
Why did you take the h bar out of the pj's right there?
Oh, because at first I just want to produce a translation and you know, if I define it like this, and if I cannot interpret P as the momentum because dimensionally it is not correct, okay? So in order to make it dimensionally correct, I just stick in some fundamental constant which makes it dimensionally correct. So without the H bar, this equation would not be dimensionally correct. With the H bar, it's okay. Okay? Just to make physics, just to make the equations conform to physics usage. You see the point?
So that PJ in the box right there is not dimensionally correct?
This is not physical momentum. This is
And
not
then you
physical.
do an H bar to make it dimensionally correct?
Yeah.
Okay.
But you see, choice of units up to us human beings. I can always choose a system of units where H bar is equal to 1. That's called a natural system of units. Then you don't have to. In fact, high energy physicists do that all the time. Because in high energy physics, the fundamental constants, there are just two: speed of light and H bar. Okay, speed of light has to do with relativity. H bar has to do with quantum mechanics. So high energy physics uses relativistic quantum mechanics. So in all the equations, the C and the H bar should be there. But if they're always there, why don't we choose a system of units so that both are equal to 1? That's called a natural system of units.
So that's relative to the natural system that PJ.
Okay. Or if you think about, this is like graduate school units, where H bar is equal to C is equal to 1. This is kindergarten units, where H bar is the units of so many joules second, and so 6 times 10 to the minus 27, and all those other numbers, and so on and so forth. So instead of 6 times 10 to the minus 27 joules seconds, I say this is 1 blah blah, a particular kind of minutes. Okay? H bar has the, remember, the H bar has the dimensions of angular momentum, right? H bar, energy times time, is the same dimensions as distance times linear momentum. It's an angular momentum. Okay? All right. So now here we are about to make a leap. I'm not going to be able to prove it to you at this point. I am only asking you to believe the plausibility of this. This expression has to do with infinitesimal translation so that I can ignore all the higher order terms. But if you look at it, this is like the first 2 terms of an exponential expansion. Okay? So therefore, by taking this mathematical leap, I'm going to claim that the unitary operator corresponding to a finite translation is going to be the exponential of this thing here, together with a minus sign. So here's the first very important result in quantum mechanics, besides this one. This one is called quantum key. Quantum key. Okay, so to change from classical mechanics, you use this key to open it up. Change the key to a derivative. Okay. Here's the second one. To write the expression for the unitary operator for finite translations, you change that expression, which only involves the first couple of terms for the exponential infinite series expansion. You have to write it as an exponential. So now, let's say for finite translations, I'm going to translate it by this finite vector, A, translate everything by a finite vector A, constant vector which would have constant components that I'm going to call AI. The unitary operator corresponding to a translation is then going to be the exponential of I over H bar, A, J, P, J. P sub j is the j component of the linear momentum. The linear momentum is just given by P sub j is equal to minus I H bar derivative with respect to xj like that. Okay? And you have to do translations in all 3 dimensions. That's why j is sum over from 1 to 3. That's so. Now, what is meant by an exponential of a differential operator? That's a little tricky question, but let me not go into details at first. But just recall for you one fact, that all linear operators can be represented in terms of matrices. Okay? So when you do represent a linear operator in terms of a matrix, this becomes an exponential of a matrix. And it goes back to what we were talking about this morning. Okay? And it's meaningful, at least that expression. This exponential of any matrix always converges. Okay? So it has a clear mathematical meaning. All right? And so this is, and you can, because of the I in here, this makes it a unitary. A unitary matrix or expansion means that the inverse of the operator is equal to what is called a Hermitian conjugate, which is if you think of it as a matrix, it's a transpose and then complex conjugated. So that this is the generalization of an orthogonal transformation. An orthogonal transformation is where the inverse is equal to the transpose. A unitary transformation is where the inverse is equal to the transpose complex conjugated. Okay? It's all the same thing, basically. The orthogonal matrices are only defined for real matrices, right? So that an orthogonal matrix, which is required to be real by definition, is such that its inverse is equal to its transpose. But for Hermitian matrices, which are in general complex matrices, the inverse. If a complex matrix satisfies this condition, then the matrix is said to be unitary. And correspondingly, the linear operator is said to be a unitary operator, and unitary operators are of fundamental importance in quantum mechanics.
Yeah. So we have this expression for the operator, an exponential of a differential operator.
Yes.
When we apply the adjoint to it, obviously it would change the sign of the I.
Yeah,
Would it
plus
play?
I.
Would it play with the indices?
Because if U is this, then you can prove mathematically that this is equal to exponential plus phi over h bar, aj, pj. Why? Because pj is Hermitian. So therefore, pj itself is such that p is equal to its Hermitian conjugate. So if you take the Hermitian conjugate of the whole thing, anytime you take the Hermitian conjugate of the whole thing, it's kind of like in complex numbers, you change I to minus I. Okay? So this guy is already Hermitian, and everywhere you see an I, you change it to minus I, and you change the operator to its Hermitian conjugate. Okay? An operator is unitary when the Hermitian conjugate is equal to its inverse. It's a special requirement. It's a generalization of orthogonal transformations. So you can kind of think of it as like a rotation in complex space, if you want to, because it's like an orthogonal transformation in real space. An orthogonal transformation, you know, is one that preserves lengths of vectors, and so it can be a rotation. Okay? It's useful to keep all these mathematical concepts in mind alongside the physical concepts that we are working with, because this is a class in mathematical physics. We always like to make this association. Yeah?
The components J's are all real.
Yeah, those are translations in real space. Okay, so all the three components are real. All right? And this time, as distinct from that situation, the epsilons are supposed to be infinitesimal quantities. Here, the a's are finite quantities. All right? So that you actually have to use the exponential expansion, keeping all terms of all orders, right? If the a's are tiny, if you just work with a tiny translation in here, obviously this is not too different from the identity transformation. Okay, this tiny thing just changes the original wave function just a little bit. And that little bit has to be proportional to the little quantity in here, right? Because this is proportional to epsilon. Epsilon is little, so therefore it's just a little change. Okay? It's not too far from the identity, so to speak. All right? Okay? So, now that we have worked with translations, before we go, next thing we're going to do is to obviously move on to rotation, see if we can play the same game again and find out the unitary operator which corresponds to a rotation. And before we work on it, you can almost guess what that is going to look like. Rotations, a particular rotation, just like a translation, would have to depend on three constant quantities, the three angles describing a particular rotation. And the three operators in here would be the components of the angular momentum operator. And that's what we're going to try to prove next. Okay? So now, so let me write down the result first so that you can see these things right next to each other to help you remember what it is that we are talking about. Now, you can also write this as an ordinary vector notation, this is like the vector A dotted with the vector P, all right? This is A1, P1 plus A2, P2 plus A3, P3, okay? P1, P2, P3, again, are the three components of linear momentum. A1, A2, A3 are the three components of the constant translation vector. Now, if you go to rotations, how do we specify a particular rotation? One convenient way of thinking about it is any rotation can be thought of as a rotation about a certain direction through a certain angle, okay? So let's say I want to rotate about a certain direction, which is represented by this unit vector here. To specify a direction, I just need to specify some unit vector. Let me call it M, okay? And supposing I want to, let's see how to write this. I want to describe this rotation by, a rotation about this axis and rotating it in the positive right-handed sense by an angle theta. Okay. Then I can describe this rotation by a certain vector which has magnitude theta, which has direction n, like that. This describes a particular rotation. Okay? And then you can guess that the unitary operator that corresponds to this rotation, I'm going to write it as m theta. It rotates about this particular direction by a certain angle. Can you guess what it is going to look like?
Minus I over H bar, theta I, L, stuff I.
L1, L2, L3 are the three components of the quantum mechanical angular momentum operator. And L is still a differential operator. Why? Because L, whether in quantum mechanics or actually in classical mechanics, we'll just look at it like this first, okay? This involves L1, for example, is, let me write this as X. Okay, the cross product. L1 involves X2, P3, and X3, P2 by the rules of the cross product. Now, P1, P2, P3 are ordinary derivatives, so therefore this makes the angular momentum a differential operator also. Okay? So therefore, you can still use this to operate on a certain wave function. And, in principle, you need to take all terms in this infinite series expansion, and if you succeed in doing that, then you produce a different wave function, which is rotated from the original wave function. But since it's a scalar wave function, it still has to satisfy this condition where if you have a mountain in here, but if you use one set of coordinate system, the coordinates are x. If you rotate the whole coordinate system, the new coordinates are x prime, okay? One and the same vector gets represented by different components in two different coordinate systems. And still the requirement of scalar properties of transformation is like this. And you can prove, as we're going to try to show next, that the unitary operator corresponding to a rotation is like this. It's very easy to remember. It's an exponent. The units are consistent because a distance times momentum is the units of an angular momentum. So h bar is the units of angular momentum. And you know that anything which sits inside the arguments of an exponential function has to be dimensionless, right? So similarly, this thing has to be dimensionless. It is because why? L has dimensions of h bar because L is an angular momentum, and this is h bar. Theta is just an angle, so many radians is dimensionless. So therefore, it's all dimensionally consistent. Okay. If you're a high-energy physicist, very often you just take h bar equal to 1, get away with the clutter, okay, so to speak. And at the end, if you're used to this, you would know how to put it back in order to make the equations dimensionally consistent. Now, before we go on to the angular momentum, let me just say something about the P first. The P is defined so that Pj is minus I h bar Pj, right? Because now in quantum mechanics, the P is no longer a number, but an operator. Then xi and pj as operators do not commute. Do not commute. In classical mechanics, the two quantities, both being numbers, would commute. xp is equal to px. But in quantum mechanics, it doesn't. X does not commute with p, and this is the basis of the so-called uncertainty principle. those non-commutation relationships in quantum mechanics are the mathematical descriptions or manifestations of the physical situation of uncertainty. Okay? I'm not going to go into that in detail because it's not a quantum mechanics. Okay? Not a quantum mechanics course.
Is that where we use the Schwartz inequality on the inner product?
No, you don't have to do that. One of the exercises asks you to asks to prove the commutation relation. This is equal to I H bar delta I. Okay. It's an exercise and it's very, very easy to prove. You can use this. This is an operator, so it's x I p j operating on some function, and you subtract that from p j x I still operating on some function. Okay. But here, because Pj is a differential operator, it operates on everything sitting to its right, if you interpret it as an operator acting to the right. Okay? Here, the Pj only differentiates the psi, but here the Pj differentiates both the x and the psi, and therefore the two things cannot be equal to each other. There's a term that's left over. That leftover term is this one. Okay, it's very easy to prove. That's why I left it in this exercise. The solution has been sent to you already. So, if you can't work it through, be sure to look at the solutions and be sure to understand why that is so. Okay? How many of you have seen this relationship in here? Some of you I bet have. Okay? That's a famous non-commutation rule for position and momentum, which will lead as a mathematical consequence that delta x times delta p is bigger than or equal to h bar divided by 2, something like that. Okay? So that's a mathematical description of the uncertainty principle. If those two things commute, then there would be no uncertainty principle. And that's a situation in classical mechanics. Okay? The uncertainty principle means that you cannot determine by a simultaneous measurement of position and momentum, you cannot determine those two things simultaneously to an arbitrary degree of accuracy. If you know one very accurately, the other one is necessarily known only very inaccurately. Vice versa. That's the uncertainty principle. Okay. All right. Now, obviously, x does not commute with p. Now, it does commute with I is not equal to j because of this, right? So if you have x1 and p2, they would commute. Okay. It's only the same components that don't commute. So x2 does not commute with p2, x1 does not commute with p1, and so on and so forth. x2 commutes with p1. Okay, x1 commutes with p3 and so on and so forth. On the other hand, all the different x's commute among themselves because x operating on something in quantum mechanics means coordinate x multiplied by that something. So x operating on a wave function is just like multiplying that function by x. Okay, if you try to be very, very kind of mathematically rigorous and you write this thing as an operator operating on some function, by definition is equal to the number x times that function. That's all. Okay, so this is known as a position operator. In quantum mechanics physics textbooks, you don't write this because it's understood to mean this. In a mathematics book, you distinguish between the two. Now, it's not entirely easy to define mathematically the position operator. To do it strictly, you have to involve the Dirac delta function and so on and so forth, which I'm not going to go through at this point. Okay? We gloss all those things over in the beginning quantum mechanics class. Okay? And similarly, the p's commute among themselves. The x's commute among themselves, the p's commute among themselves, but the x and p don't commute. So these are the important non-commutation, so-called commutation relationships for quantum mechanical operators. Okay. Now you know that in classical mechanics, a dynamical variable is always a function of x and p, right? In classical mechanics, and therefore you can quantize it to turn that dynamical variable for the Hamiltonian. The Hamiltonian is a classically mechanically is a function of position and momentum, right? And so you use the quantum key and change the momentum to a differential operator, but the x still remains multiplication by x. And you turn that classical Hamiltonian function into the quantum mechanical Hamiltonian, which is the thing that sits in the Schrödinger equation. So that's interpreted as an operator. So you know that it's Hamiltonian is supposed to be sum of the kinetic and potential energy. So for a single particle, it's p squared over 2m plus potential, like that, right? And so if p is minus I h bar gradient, and this thing gets turned into minus h bar squared over 2m the Laplacian times p, which is just a multiplication thing. So this is called the quantum mechanical Hamiltonian operator. It's no longer a function. It's an operator because the p has been turned into an operator, being a differential operator in this case. Okay? But now you see why it is that the p is dBj, because p is the translator, infinitesimal translator, so that it then involves a derivative. That's the reason why the derivatives come along. This is a so-called, what is it called? The coordinate picture representation of an operator in quantum mechanics. There's something you do a Fourier transform, then it becomes a momentum picture representation of an operator. Okay. All right. All right. Now let's go to angular momentum, right? For angular momentum, things are just a little bit more complicated, and it's time for us to take a little break. Okay. At this point. All right. We'll take a 5-minute break.